Thank you for the invitation. Yeah, really a pleasure to come here to share some recent work. So we have been focused on trying to develop this new imaging technology for Positronium nighttime imaging. I know so many of you may not be aware of this, and the same a few years ago, I wasn't aware of this either. So I learned quite a lot in the last few years about positron annihilation. So as we all know, so people working in PET, so we inject this radioactive tracer into the patient and they will emit the positron. My initial understanding is actually on this slide right now is the positron is the antimatter of the electron is going to annihilate with electron nearby, so producing the 2511 TeV photons. That's how we detect the signal and reconstruct the tracer activity distribution inside the body. But it turned out this is not the complete picture. Before this annihilation occurred, there's a substantial, you see this one word, there's about 40% of the positron actually going to form a positronium. Essentially, it's an exotic atom, so short-wave atom formed between a positron and an electron, so they're orbiting around each other. And there's two types of positroniums. Depends on their spin relationship. So the anti-parallel spin, that's called positroniums. So PPS, this one has a rather short half-life, so about 125 picoseconds. So it's going to annihilate almost immediately, so generating two photons coming out. And a third, three-quarters of the positronium has a parallel spin that's called autopositronium. And this one has a rather long half-life, so 142 nanoseconds in vacuum, and it's actually produced three photons coming out. And because of this rather long half-life, so 42 nanoseconds, it allows this autopositronium to interact with surrounding tissue. And it's actually mostly inside the tissue. Its annihilation occurs through interaction rather than self-annihilation. There's two types of interaction. So one is a peak-off annihilation. Essentially, the positron, rather than annihilating with the electron inside the positronium because it has a parallel spin, it's actually annihilated with a nearby electron and the anti-parallel spin. So that's much easier. And the other one is called spin exchange. And this is actually the interaction pathway mostly affected by oxygen concentration. Basically, there's a spin exchange with the electron inside the oxygen that will flip the spin from parallel to an anti-parallel, so then therefore able to annihilate very quickly. So therefore, inside the tissue, the half-life, the lifetime of autopositronium is roughly estimated to be around 2 nanoseconds to 4 nanoseconds. So that's really much shorter than 142 nanoseconds. So really this gives us information about oxygen concentration and also the tissue structure. So the availability of the electron available to perform this peak-up annihilation. And those are the information we want to extract by measuring this positronium lifetime in vivo to get an image, and then we can see what's the microenvironment of the tracer surrounding the positron annihilation. So here's some a human study. So using glioma patients, locally injected tracer fairly high concentration. So what it shows is that inside the glioma tumor, it has a shorter lifetime than the normal brain tissue. Okay, and this one shows the average lifetime. So that's just the average over all the pathways, not the autopositronium. The image shows also positronium lifetime. So both of them are useful. So we will come back to the mean lifetime later. And also there is a study to measure the lifetime annihilation rate is actually linearly related to the oxygen concentration. So that's give us hope that we can use a positronium lifetime to measure oxygen concentration to detect hypoxia for cancer treatment planning. Yeah? So what do we need to do this imaging? For this technique, What I'm going to describe is really rely on the radio tree isotope give us a prime gamma to tell us when the positrons are being emitted. Of course, there's other approach by detecting the triple three-fold annihilation fraction. You can also measure, estimate the mean and lifetime as well, but that's not what I'm going to talk about here. The second one is the instrumentation. We need to detect this triple coincidence. So among the prime gamma and 2.511 keV photons, essentially, those are what we detect in a traditional pad, and this is the extra detection we need to form. And by measuring the time difference between the prime gamma and the 511 keV, we will get the time delay, and by using those two photons, we can reconstruct the spatial distribution. And this is really pretty much solved by the development of long-axis field of view scanner that Simon described yesterday. So the total body scanner that's being used for this purpose. My talk going to focus on the third component. It's really how we reconstruct the image and to get the spatial distribution of the Positronium vector. 17. And also what happened. So this is a lifetime model. Okay, so we have 3 photons. We detect 3 photons, but really the event, the data we're going to keep, that's including the position of the 2.511 keV photons. That's we call the LOR. That's the standard information we have in the PET system. With the time of flight information. Additional information is the time delay between the pulse gamma and 511 keV photon. That's calculated by this formula. And in fact, if you just want to make sure you realize the location of the prime gamma detection doesn't matter once we can calculate this time delay after compensating the travel distance, travel time. So the prime gamma, we only need to calculate the time delay, not to detect a location. And this on the right side, that's a time histogram of the time delay. So basically, it's a count as a function of time delay. And this can be modeled as a multi-exponential modified Gaussian distribution. So we have a Gaussian distribution as a detector response. And then we have this exponential, multi-exponential to model each pathway. For every pathway, there's an exponential distribution. So A is the fraction, and the lambda is the decay constant. And those are the A and the lambda are those unknowns we want to estimate for every pixel. So of course, so there are some existing methods available already, and this was based on two-step process. The first is using the time of flight information to localize the events, and then just perform. So for example, here there's 4 point sources far away from each other, so you can kind of use the time of flight to localize the events and then fit the time histogram to estimate the also Positronium lifetime inside each tissue. The problem with this is the spatial resolution is limited by the time of flight resolution, and based on the simulation, if we consider a 3-dimensional backpropagation, you get 3 centimeter for 500 picoseconds timing resolution, and if you want to get 5 millimeter resolution, that's what we require. And that requires, the estimate was 50 picoseconds timing resolution. Okay? So this one really you kind of discourage people to develop this technique because people feel 50 picoseconds timing resolution is still not available yet. Okay? But what I'm going to show you is we can actually get this resolution, so better than 5 millimeter even with the current time of flight system. Of course, so for people sitting here, we all know it's not that hard to formulate the problem once you can write out the likelihood equation, right? So we basically write the likelihood equation here. We only have the lambda, so that's the focus. So for the lambda, essentially we can write out as a time histogram, and then it's multiplied weighted by this fraction calculated from based on each emission from each pig's voxel. Okay, and the X is the activity or the tracer concentration that we can estimate using the standard PET reconstruction. So this still requires the regular PET reconstruction first. And once we have this likelihood function, we can derive a maximum likelihood estimation. So you can use a gradient descent method, so obviously, but what we did is to derive closed form monotonic update equation. So this one was only for the model exponential model, so very simple, that's what we started. But it's a very nice formula, so it almost looks similar to the NLEM algorithms, but with a little change on the numerator and the denominator. But the formula carries the similar spirit of the NLEM algorithm. The only drawback, so everything is beautiful in terms of maximum likelihood estimation. The drawback is the computation cost is very high, so there are some details in terms. This calculation here essentially involves the back projection for every event in terms of back projecting changing the system metrics. So that's another calculation, far more than the least small reconstruction in PET reconstruction. And so that's a limitation. So therefore, this one was not capable to perform real reconstruction. We did some simple simulation 2D, but that's it. Okay? The real breakthrough was really come from by my student Baomian. I should mention this work was really a collaboration with between Baomian and myself. So what he developed this method was, it's called, so we gave a name called SPLIT, so statistical Positronium lifetime image reconstruction will be a time thresholding. So the basic idea is we actually divide the data. So based on the time delay, this is measuring time delay in the unit of nanoseconds. So we just apply a series of thresholds and partition the data into subsets. And for each subset, basically that's just count data, and then we can use the OSEM to reconstruct the image. That's just a standard PET reconstruction. And after that, we get a series of lifetime cut image that we can actually plot the time, almost like a time activity curve in the dynamic PET, and then just fit this integral time using the integral of the likelihood model. Okay? The beauty of this is that we requires a standard OSEM reconstruction, and also it's very flexible with the model we're going to use and practical for 3D data. And well, in fact, if you think for some people, you can see there's a lot of similarity between the lifetime reconstruction in this framework versus the frame-based dynamic PET reconstruction. Okay, but it took us a little time to reach that aha moment to realize, okay, we can actually solve this fairly simply once we make that analogy. Okay? But initial development was not obvious. Okay. Of course, this model allows us to calculate, okay, how many time frames do we need? Okay, so this is a criminal lower bound, and the horizontal line at the bottom, that's the continuous, least small likelihood criminal lower bound. And then the two curves shows as the function of number of beams, what's the main variance we can achieve. As you can see that we need about 20 to 50, 20 to 100 beams to achieve that bound close to the least small data. And of course, if we use a non-uniform beam, that's a Fock-Howe normalized beam, that's give you a little better variance with the fewer beams, but once it's reached some larger number of beams, it doesn't matter which method we use. Okay, so we can do this reconstruction. So we did the simulation 3D, so a fully 3D simulation of the neural explorer with a large small animal. I mean small animal, so 18 centimeter across, 5 centimeter wide. Okay, and simulating the PSMA, gallium PSMA uptake, so higher uptake in kidney, liver, and then there's a tumor should have higher uptake. And then a lifetime differs, so tumor has a lower lifetime and everything else has a little higher lifetime. And we can run this reconstruction. So here, the left side is the activity image. Just show you it's not a uniform activity. Okay, so but that's not very interesting. The part is really on the right side. So that the first picture shows the ground truth lifetime image, and the middle is the direct time of flight back reduction methods. That's the traditional methods using the maximum likely point reconstruction, and then do the fitting. And the last one is the split reconstruction. Okay. Obviously, you can see this is much noisier, but also actually not only this is noisier, but also has larger bias, as you can see from this bar graph. So for the region where the lifetime is uniform, well, the bias are comparable. So it doesn't matter how blurry your image is, the lifetime is uniform, so you don't introduce much bias. But for the lesion that is small, you can see the traditional methods has large bias because the resolution is limited. I mean, the prediction was right for that particular reconstruction methods, but with our methods, the bias is much smaller. And also, you can see across all the regions, the standard deviation is much lower. Okay. So that's all good. But the reconstruction still takes time. So it takes 50 frames to reconstruct and then to do the fitting. So it's time consuming, just like doing a kinetic pixel-wise kinetic modeling for the total body map. So we want to make it faster. This is another development. So we develop faster methods. The first one is actually only reconstruct the average lifetime or the mean lifetime. That is basically the average, just the first moment, the average across all three pathways. And I want to bring this picture back again. This is from the human measurement. It actually shows the mean lifetime actually has a better signal-to-noise ratio to differentiate between the glioma and brain tissue than auto Positronium lifetime. Just indicate it's actually useful. That's so to reconstruct this, it's much simpler than the previous one. Okay, and that's why the method is has acronym simple. It boils down to essentially two reconstructions. Okay, the bottom is what we are familiar with the standard OSEM reconstruction. Just using the least mode reconstruction. If you don't want to do least mode, that's fine. Whatever reconstruction you get, so that's the activity image we get. The change is on the top one. It's a modified OSEM reconstruction. The only change is this red one, top K. In the standard least mode reconstruction, every event has a weighting factor of 1. Here, every event has a weighting factor equal to the time delay. So that's the only change. And then once you reconstruct both images, you just take the pixel-wise ratio. Let's give us the average lifetime. Very simple. And that's the same data, just the different reconstruction methods. So now they just show the average lifetime. So they are lower than the auto Positronium lifetime. So the methods actually achieve very close to the ground truth value, much better than the previous time of flight by projection methods. Okay. And then we apply this to ex vivo data. So basically, we bought a RBI state from the meat market and then put it inside the PET scanner, and then we radiate that tissue with a sodium-22 source suspended on the top, so that we can have a positron annihilation on the surface of this meat sample. That's activity image. You can see the non-uniform distribution just because of the solid angle effect. And on the right side, that's a lifetime image. You can clearly see the difference between the separation between the fat and the muscle, because fat has a larger void space between the molecules, right? So it has a longer lifetime. Okay, so that's for the average lifetime. So can we do auto Positronium lifetime imaging using this simpler methods? Okay, the answer is yes. We can actually extend this to a higher order of movements. So consider the mean lifetime. It's just the first moment, right? So you have the n power equals to 1, that's a mean lifetime. When you have n greater than 1, that's a higher moment. And for this exponential modified Gaussian distribution, the moment of the distribution can be computed from the moment of the Gaussian distribution as mu, and the moment of the exponential distribution as g. And the mu is known, okay, because that just comes from the normal distribution with a known standard deviation and shift. It's the moment of the exponential distribution that contains the unknown that we want to estimate. Essentially, once we confirm this moment images, and then we can formulate a set of equations and solve those unknowns. Okay. So the first thing is how we get those moment image. It's just a simple extension of the simple methods. So previously we reconstruct the average lifetime, so we just have a weighting factor equals to tau k, and now we want to go to n moment. We just have raised the power from 1 to n, and then still take the ratio. So there's actually, because this one is already reconstructed, so we only need one reconstruction to get the nth moment. Once we get a moment image, right? So here, if we make further assumptions, so just assume the lifetime of the Dirac and the Positronium annihilation are known because they are very short, less affected by the tissue environment. So we can consider those are known, pre-estimate, and also the ratio between Positronium and Positronium based on the spin statistics. So that's a 3-to-1 ratio. Once we fix those two, there are only just two unknowns. We need to estimate one is the Positronium lifetime, the other one is the fraction. So we only need two moments. So we get first and second moment image. So remember first, which is the average lifetime. And from those two moments, we can calculate the exponential distribution moment. This is called deblurring process. And then from there, we can calculate the lifetime and fraction using those formulas. Essentially, for the lifetime, it's a quadratic equation. So that's a very familiar solution, right? So the A, B, C are given there. Don't need to read the details, but just believe me, so those are all closed form equation. There's no fitting involved. So very straightforward. And we can apply this to the simulation data. We can show, the moment methods, and it gives a comparable result as the previous split method with all the fitting and the reconstruction. In terms of theoretical performance, that's a femoral lower bound again. So the horizontal axis is the number of beats or number of moments. As you can, so those two, the dashed line are the beat methods, like a split. And then the solid line are the moment methods. So there's a power moment, that's what I described over here. So we only use two moments right now. So of course, you can reduce the variance by using more moments. The problem is there won't be a closed form solution. Okay, if we have more measurement than unknowns, or we can use actually, once we don't require closed form solution, we can actually use other weighting function like exponentially weighted Laguerre moments to reduce the variance as well. So there's a lot of options there. That's one place the AI can help to find the optimum weighting function. Just a couple minutes show you the real data on a human scanner. So this is a collaboration with Joe Cart's group, acquire some phantom and data. So three radioisotope that we plan to use in humans. So the first two, rubidium and gallium, already available for human imaging. Stadium, that's almost the ideal type of isotope because it has a lot of prime gamma emission, so 94%, but still need to get FDA approved for human clinical use. So right now we just do some phantom studies. So on the left side shows the energy spectrum just to tell you should see the peak of each individual curve for the prompt gamma. So the first peak is 511 keV, the second peak corresponding to the prompt gamma, just to show you we can clearly distinguish the prompt gamma and detect the prompt gamma and distinguish from 511 keV photon. And on the right side, that's the time histogram. You can see the yellow is a scandium, so the time histogram is less noisy than others. So the The blue one in the middle, that's a rubidium scan, and the red one, the most noisy one, is the gallium scan. So that's the reconstructed image of the cylinder vacuum with a polycarbonate slide in the middle of the radioactive solution. This polycarbonate has a longer lifetime than the water. So that's what you can see. Okay, even though there's no positron inside the polycarbonate, the positron range will allow the positron annihilation to occur inside the polycarbonate. So the top row shows activity, so that you see very low activity inside the slab. But the lifetime on the second and third row shows the lifetime of polycarbonate is really high. It's higher than the water. Right? At the bottom row is apply the kernel-based filter to the middle row lifetime image. Yeah, so that's what's kind of what you can achieve with you can achieve better images with other AI techniques. And the measured resolution is around 4 millimeter, very comparable to the past image. So, okay, yeah. So that's just to summarize. So just already show you this reconstruction methods we have developed, and also demonstrate we can perform this on a human scanner and achieve comparable resolution as a standard CAD. The goal is really to perform this simultaneous PET and positronium lifetime tomography on human, and just to investigate the potential of assessing the disease, specific tracer uptake, as well as the tissue microenvironment. And of course, the future work will use AI, try to reduce noise, and develop faster and efficient reconstruction methods. Just some acknowledgement. So again, a lot of work are performed by Biomedical, and also with a contribution from a few formal lab members to build a software platform, and also mobile kernel-based reconstruction and the kinetic data fitting. And thank you, Simon, and the PAMI team and collaborators. Thank you for your attention.